Afternoon, everybody who was able to dial in. We're going to have, I want to say this is like maybe six or seven for this group. It's one of our yearly talks from the team at the University of Michigan, who work on perfSONAR plugins. And in particular, this one is going to be focusing in on some of the pSSID work, which is a series of tools that are used for monitoring Wi-Fi metrics. I know that there's been some improvements due to the recent release of perfSONAR 5. So the team this time around is Ed and Dianlu and you, and they're going to walk through some of the new improvements to this tool. And I was told that if we're nice enough, they may even do some demos for us. So I will turn it over to Ed to get us started.
Hi there. I'm Ed Colone. I'm a software engineer at the University of Michigan.
My name is Dianlu. I'm a graduate student from Eastern Michigan University. And this summer, I work for the network infrastructure and IDS and working on the pSSID project.
Hello, everyone. My name is Yu. I'm a graduate student at the University of Michigan, majoring in computer science. And this summer, I'm also working on the pSSID project with Ed and Dianlu.
Thank you. So let's see. So as Jason sort of alluded to before, this has been an ongoing project. And in fact, I see one alumni that used to actually work on this project is also on the call. Hi, Abigail. And a little bit of history. So when this topic first came up at the University of Michigan, I was asked if we could put together some sort of Wi-Fi monitoring system. And my famous last words were, how hard could it be? Well, it ends up being extremely difficult. We had a lot of lessons learned. Layer 2 connectivity is very difficult. Usually the normal usage case is they set it up once and they never change it. Our usage case is that we're constantly flipping between SSIDs. Layer 3 is difficult as well. You have a lot of chances to mess up your routing and your DNS. We've had DNS issues. We fought with network managers. We've had many permutations of routing algorithms and different problems with each one. We've discovered that some of the software and some of the techniques were incompatible with some of the OSs we were using. perfSONAR integration has been non-trivial, and we ended up having to describe our monitor a very complex config file. So that ended up being non-trivial to configure and deploy to all the probes. We did a field trial of some of our earlier efforts, and that proved unstable. So we had to go back to the drawing board and reinvent some of the technologies. Through all of this, we've managed to get a little interest from other institutions. Virginia Tech has collaborated with us, and thankfully, because they came up with some really good ideas and some software enhancements we dearly needed. We've continued to work the problem, and we've finally made some breakthroughs and are getting very consistent results. I'd say we're ready for our alpha field deployment, and it's possible that if other institutions wanted to try our solution out, that it's stable enough that I could recommend it.
So modern Wi-Fi networks usually use multiple access points to provide comprehensive coverage and connectivity. And U of M, for instance, we have several SSID like Edge Room, M Wireless, and also M Guests. So each one of them serves a different purpose and is available simultaneously. And there are more than 17,000 AP campus-wide. This redundancy of Wi-Fi network not only satisfies the needs of students, faculties, but also visitors and residents nearby. So a large-scale network like this, by nature, is very complex infrastructure. For instance, Wi-Fi network operates on different frequencies, um, bands to manage traffic and reduce interference. different SSIDs may have a specific policies that affect the performance, such as bandwidth allocation, access priorities, and usage limits. For instance, Azure Room might offer higher priority and bandwidth for academic users compared to MGuests. Next slide, please. As we all know, a strong signal does not necessarily equate to a good and reliable network experience. Usually, complete outages in network connectivity are straightforward enough to identify because there is no signal or connections at all. Even with a redundant infrastructure, a strong signal might mask underlying issues. Individual access points of network components might also fail without affecting the overall signal streams. That's a good signal does not always guarantee that all the parts of the network are functioning properly. A very good example is that problems may occur between the access point and the core network infrastructure. Even with a strong signal, issues can still arise when connecting to external networks or the internet. Another thing is problem may arise with user authentication or authorization, which may also disrupt network access despite strong signal strengths. This is part of the identity and access management system. So it is quite critical to benchmark the actual network performance and user satisfaction rather than relying solely on this signal strengths. pSSID is an open source software developed at the University of Michigan in collaboration of Virginia Tech. It is a Wi-Fi SSID testing scheduler that used in the tools developed for layer 2 and layer 3 connections. It also comes with a GUI for provisioning and configuration. It also offers data analytics with dashboards and alerting capabilities. Since we employ Raspberry Pi 4, which is a low-cost hardware, it is ideal to distributed deployment model for a large-scale campus like U of M. It is written mainly in Python and use commodity open source infrastructure like perfSONAR and Ubuntu.
So now I'm going to talk about the entire architecture. So our system has three major components. There is a front-end GUI controller or dashboard, and the second component is a collection of Raspberry Pi Wi-Fi probes. The first component, the GUI controller, will provision and configure the Wi-Fi probes, and then the Wi-Fi probes will perform the tests and gather the metrics, and then we're going to send the metrics to the third component, which is a dedicated data server for data analysis and visualization. So the rest of the presentation will be as follows. I'll talk about the first component and the third component, and then in the middle, Lou is going to come back and talk about the second component. One thing to note here is that the second component, which is the collection of Wi-Fi probes, it is scalable. So if we scale up the Wi-Fi probes, we might also need to provision more data servers for data analysis and visualizations in the future. So that's something we can consider and improve in the future. So now this is the first component, which is the GUI controller. Before we look at the details, I'd like to first talk about the development and deployment processes. So during development, we have a dedicated development environment. We have developers working on the project. So after a certain phase of development is done, they can run a simple Ansible script called build and publish to first build container images, Docker container images out of source code, and then push or publish the container images to Docker Hub. Next slide. When it comes to a user, they want to provision their own pSSID controllers. They can run another Ansible script, which is install and configure, which will first fetch container images from Docker Hub and install and run the Docker images on the pSSID controllers they want to host the system on. So other than using Docker, we also provide a traditional deployment method with source code and GitHub that is also available. So now this is the architecture of the GUI system. On the top, the core application has 3 Docker containers, a client, a server, and a Mongo database. A user, which in this case is a Wi-Fi admin, directly interacts with the client container. So they can configure the GUI dashboard, they can create or define a list of hosts, and then they can define a list of tasks. Then the client container will talk to the backend server and MongoDB containers. So thanks to Docker, the data of the entire GUI dashboard or the GUI state is persistent on disk. So if we want to back up the data state of the entire dashboard, we simply need to back up the Docker volumes. So in addition, we also have some test templates, which are files on disk. We use them to define tests in the entire system. And further, we use tests to define jobs and batches, which we eventually schedule on the probes. The output of the web application has 2 major files. The first one is host.ini, which is a list of available probes we define in the dashboard. So it's essentially saying which probes are available to run some tasks. And the tasks themselves are defined in the pSSID daemon configuration file. So after these 2 files are generated, we can run the provisioning script to run Ansible and copy the daemon configuration file to all the target hosts we defined in the host.ini file. A thing worth mentioning right now is for security reasons, right now we don't directly run the provisioning scripts with a button push in the front end, but that is definitely something we want to do in the future. So right now we still require human intervention to come in manually and run the provisioning scripts on their own. But also we've provided the hook or the possibility to automate the entire process in the future after we address the security concerns. Now this is the overview of the daemon configuration file. The core component of the configuration file is batches. To utilize the perfSONAR batch processor functionality, we don't want to run raw tests or jobs on the probes. Instead, we first use test template files on disk to define tests, and then we use tests to define jobs. And we use jobs, schedules, and SSID profiles to together define batches, and eventually we schedule batches on the target hosts. A feature here is metadata, which is essentially just a variable in the configuration process. I will explain the details later, but the key spirit here is it's going to save us a lot of work, and we don't have to write a lot of duplicated batches with only small or trivial differences. Metadata is defined on the hosts and groups pages, and eventually we can consume or use them on the test and batches pages. All right, so this is the first page of the GUI system, the host page where we define and manage hosts. For each probe, we can define it either using their IP address or host name. We can assign batches to individual hosts. We can have 0, 1, or more batches assigned to a host. So now we can define a metadata for individual hosts. In this example, we have pi 198, 111, 226, 182, and the metadata or variable we define is test iFace, meaning test interface, and the value is WLAN 0. An interesting case here is that the 182 probe, it's possible that it belongs to a group that also has the same variable test iFace defined. And it's also possible that that group has a different test interface value. So let's say 182, the host itself, has test interface WLAN 0, but a group it belongs to has test interface WLAN 1. So we have a conflict in metadata here. In this case, metadata defined for individual hosts take the highest precedence. So we're going to use WLAN0 as the test interface for this host. The second page is about groups, where we define and manage groups. Same as for hosts, we can also assign multiple batches or 0 batches to a group. And then all the hosts within the same group will run all the batches assigned to this group. We can also define or assign metadata to a group. Another interesting case here is it's possible that we have 2 different groups that have the same metadata defined, for example, test interface, and they have different values. One of them has WLAN0 and the other has WLAN1. And then, although unlikely, it's possible that both groups contain the same host, in which case this host will have conflicting settings for test interface. One of the group it belongs to has WLAN0, the other has WLAN1. So we have another conflict of metadata. In this case, behaviors are undefined, and this is something we definitely want to avoid doing. A handy feature here is regular expressions. We can use regular expressions to define a group that match either the host name patterns or IP address patterns for all the probes. The third page is schedules, and we use cron expressions to define schedules. This is very precise and flexible, and a batch can also have multiple schedules. A common use case is, let's say, for example, we have a classroom, we have a Wi-Fi probe in the classroom. We have a routine schedule at, let's say, Sunday 2 a.m. when there's nobody in the room. We want to test the Wi-Fi performance then. We have a separate routine schedule, let's say Monday 10 a.m. when there's a lot of people in the room and we want to test performance again. And maybe a professor came through and said, I have a class at Tuesday morning, and I noticed that there's a Wi-Fi problem at 9:15 a.m. every Tuesday morning. So we can have a special schedule just for Tuesday at 9:15 a.m. So it's helpful and intuitive to have multiple schedules for the same batch. This page is SSID profiles, where we define SSID profiles. The key thing to note here is for each SSID profile defined on this page, we need to have a WPA supplicant file on probe. And a batch can also have multiple SSID profiles intuitively. So for example, we first want to test the main Wi-Fi on campus, and then we want to test the guest Wi-Fi on campus, and then we want to test Agile role and so on and so forth. So we can perform the exact same tasks on different SSID profiles. Now, this is the core page of the entire GUI system, the tests. They specify exactly what we want to do and which aspects of the Wi-Fi we want to test. Currently, we support perfSONAR tests and test specs. We can also use metadata defined earlier on the host and groups pages here to fill out the test fields. The cool thing here is we use dynamic template files, again, on disk to define test rules. So when I say test rules, they're basically just specific fields for each test type. In this example, the test selected is RTT, and the test rules are dest, length, and protocol. Also, we have input validation code for each input field. So let's say in the future, we want to make a new field for RTT. The only thing we need to do is we go to the rtt.json template file on disk and make changes there. In the future, we can also get specs directly from perfSONAR, and we don't have to use our own version of templates, and we don't have to reinvent the wheels and write our own conversion code. So the jobs page, jobs are simply wrappers for tests, and we can have multiple tests within the same job.
So we can have multiple tests inside of a job. This is so that a group of tests can be run in parallel. There's also a continue if clause so that you can say if one or more of the tests inside of the job fails to complete, we can elect to not run the next job. So you can have multiple jobs, and this is a way of controlling whether or not one runs after a failure or success of the other. It also has a back off, which means that instead of launching all of the tests in the jobs simultaneously, you're able to launch them at a certain interval. In this case, it defaults to 1 second. So this is batches. Batches are where we kind of aggregate all of the previous attributes and turn them into something that we can assign to groups and to probes. So you can see here that the batch has a name. In this case, it's comprehensive. The test interface, as you can see, is using one of our metadata substitutions. It's using test iFace. So it's looking for metadata that was either defined earlier at the host level or the group level. It takes, you can select which SSIDs you'd like to run this against, in this case, just M-Wireless. And then you select which jobs that you'd like to run against those SSIDs. And this is an ordinal picker. So if you pick jobs in a sequential order, they'll be run in that sequential order and may or may not continue depending on if the continue if clause has been met. The schedule selection is, you can see here is every 30 minutes, but as you mentioned earlier, you can aggregate them. So you can have multiple schedules for each batch. The batches are all in a timed priority queue. So if you have two batches scheduled at the same time, the tiebreaker is with the priority number, where it's done like a lot of things in Unix, where the lowest priority number is ironically the highest priority. So in this case, if you had something that collided with it and the schedule and the other thing was priority 2, this one would get run first.
This slide highlights the capabilities of a Raspberry Pi, which is a very versatile single board computer that can extend well beyond its educational roles. And additionally, this is quite an important feature that it can add using third-party power of the internet head to power this device on one Ethernet cable. So it can provide streamlined power and data solution all together at once. Its flexibility in expanding more features makes it a popular choice also in the industry for a variety of applications. So in our alpha field test, we're gonna use off-the-shelf keys that includes essential features for security, such as port protection. So Raspberry Pi has a couple of ports, like a USB port 2.0 and 3.0. This case gonna only expose the Ethernet connection. So people cannot mess around this device in the field. This setup is equipped with power over Ethernet head, which facilitates power delivery and data connectivity, as I mentioned before, over the single Ethernet cable. Each unit is also provided with a 64 gig SD card to ensure enough storage capability. Very importantly, the cost for this device is reasonably under $100, making it a very efficient and cost-effective solutions for test needs. This slide shows the PC probe configuration. As you can see, we use the 1 gig Ethernet portal to perform Ansible provisioning. And the Raspberry Pi is going to be run with Ubuntu Server 22. Wi-Fi interface is going to be isolated in exclusive network namespace. In the early development, we also tried policy-based routing, but we found out in the Ubuntu system, even though you set up the priority number for the W0, which is the Wi-Fi interface, sometimes it will kind of switch between the Ethernet port and also between the W0. So there's no guarantee we can perform the testing metrics and get a reliable result from that setting up. Because we need to make sure when we perform the Wi-Fi metric testing, we only want to throw those metrics through the W0, the Wi-Fi interface. pSSID will be run as a daemon and write test metrics in system log, and which will be transmitted by the file bits from the default network namespace. pSSID also utilizes pScheduler and layer 2, layer 3 for metrics. For the layer 2 connection, we also need to provide a WPA supplicant configure file, which is essentially a profile that defines the protocols and user authentication informations. For the layer 3, 2, it's going to manage DHCP and also DNS, perform DNS management. And after that, pScheduler will do the metrics. The pSSID daemon algorithm goes like this. So it first reads the configure file pushed by Ansible provisioning and build metadata dictionary and add batches if it can find itself in the configure file. Later on, it will also try to identify itself whether it belongs to for any group association, affiliation, and then add corresponding metadata and batches. Like you mentioned before, if there's a conflict, the host will have the higher priority precedence. After that, pSSID will initialize those batches, perform variable substitution based on the established metadata dictionary. Then it will create pScheduler test specs, which is done by using a Ginger2 template to conform to the format, the input format of the pScheduler. And the batches will be scheduled based on the cron expression, which Ed mentioned is a timed priority queue. Afterwards, pSSID will enter into the testing loop and run the scheduled batch and the interval and reschedule it afterwards. Although this looks like a very simple algorithm, we need to deal a lot of things like DNS management for the layer 2 and layer 3 stuff. So as you will see in a later screenshot, that all those features are provided by pSSID daemon program, and which will enable the user to identify if one part of the system encounters an issue. The pSSID will give a warning or information out of the whole process. This slide shows a detail of the SSID testing process. So first, it will build exclusive connections for the test inside a namespace, which is going to be done by the pSSID program. It will figure out the first available Wi-Fi interface from the system and use that one and bound that interface into the network namespace. Then it will use layer 2 and layer 3 tools to establish connections. pSSID sends the batch test format to pScheduler for protocol testing. Afterwards, both layer 2 and layer 3 tools will be teared down and get ready for another round of the tests. This is an example of perfSONAR batch processing. As you can see, each batch may contain more than one job, and each job may contain more than one test. For those tests that are not exclusive, like HTTP or RTT, those tests pScheduler will figure out to run. That's a parameter we can toggle that to let the pScheduler run them whether in parallel or not. For throughput test, which is exclusive test, a pScheduler will run them exclusively. The continue if block is the one we wanted to use when you first set up this system. You want to make sure if it's working or not. Usually you can set the first job with a continue if to false, and the first job is a simple test like RTT. After run this test, you can see if the whole system is working or not by predetermining the result rather than run through the whole big test suite from your configure file. This is the physical testing architecture we're going to implement at the University of Michigan. The pSSID prop will be distributed on campus, which is connected through the Uber. And in the data center, there's going to be a switch controlling all those Uber systems. So what we wanted to figure out is if a network issue comes up, we usually wanted to determine the shortest path. So we can figure out which part of the system that is comes from the user's perspective that is not working correctly. So we can run a throughput test against the perfSONAR node in the data center and get the metrics. And further on, we can also run RTT and round trip tests against the further and farther internet services. And the data center and the Wi-Fi Uber switch are connected with two 10 gig cables, so to enable bigger like a bandwidth. So this slide shows that pSSID runs in the command line with a lot of standard output. So it offers the command line arguments you can provide. Like in this case, it provides a host name and the location of the configure file. The first thing it will do is to read the configure file, identify itself, and build the metadata dictionary. Then you can notice I intentionally leave a variable that is conformed to a form that need to be substituted. So it will read the metadata dictionary and find corresponding value, get the variable substituted. And once this is done, the batch is ready to be scheduled. When the scheduled batch is run, it first create a namespace by attaching the Wi-Fi interface into pSET. So the network namespace is called pSET WLAN 0. Then it will bound the interface to the namespace and perform layer 2 and layer 3 connection. You can see we need to deal with the DNS issue. So when layer 3 runs, it will modify the resolve config file in the default namespace. So we want to make sure, because we're going to use the 1 gig on the Ethernet to transfer the testing metrics. So the first thing we wanted to do is to copy that file to a temp location. Then after layer 3, the DHCP gonna rewrite the config file in the default namespace. But this time, this config file we're gonna use to enable the Wi-Fi connection. So we want to make sure this config file is copied to the location that the system, the network namespace is able to recognize the location in the /asset network namespace folder. Once all this is up, we want to make sure the original resolve config file will go back to the default namespace. So we have to copy it back. If everything goes perfectly, then this batch is going to be dumped to the pScheduler and run the test. In this series of process, if any one of those steps has an issue, pSET is capable to tell the user that the location, the process that went wrong. Here is a throughput test against using pSET system and in conjunction with pScheduler and layer 2 and layer 3 tools against the M wireless. So as you can see, pScheduler gonna perform a couple of rounds of tests and provide a summary of the Wi-Fi throughput test metric.
So now we're going to come back to the third component of the entire system, the data analytics pipeline. After the Wi-Fi probes perform all the tests and gather all the metrics, we're going to forward the metrics using file beat to the data server. On the data server, we want to mimic what perfSONAR does. So we use an ELK stack, but instead of using Elasticsearch, Logstash, and Kibana, we use Opensearch, Logstash, and Grafana. So Logstash will receive all the metrics, and it's going to perform some preliminary filtering. This entire pipeline is completely customizable. We can implement our own pipelines and filters. After the filtering, Logstash will forward the results to Opensearch for indexing and storage. Eventually, Grafana is going to come in to query the Opensearch database and visualize the results and produce some pretty graphs and charts. So here's an example. I've received RTT test results from 2 Raspberry Pis, 184 and 179. I implemented a pipeline to separate the results. So we can see we have 184 RTT on the top and 179 results at the bottom. A common example or use case for this is we have some probes, let's say in the computer science building, and then we have some other probes in the chemistry building. If let's say the RTT results for the chemistry building are extremely high, we know something is wrong there, and we can go in there and diagnose the problem. Also, another common use case is we can monitor all results for the same probe, regardless of test types. And of course, we can go in Grafana and set some warning thresholds, and if the results exceed the thresholds or don't meet the thresholds, then we trigger an automatic alert. So that is all we have, and we'll take all questions.
As you can all see, this has been a long-standing effort, and a lot of different institutions and individuals have worked on this. And we'd like to acknowledge that. And this is just this is not a comprehensive list. We've had other people donate ideas and discussions, and this is just as some of the most obvious people who've committed stuff in development.
All right. Well, thank you all for going through that. I'll remind everybody that if they'd like to ask a question, you can raise your hand or type it into the chat. Um, I'll also allow you to unmute yourselves if you just want to ask. I have a couple that I jotted down during your presentation here. So you said that you're almost ready to perhaps allow other institutions to help you with alpha testing or beta testing. Uh, can you flash up maybe an email address or something really quick so that if people are interested in that, you could they can contact you?
Oh, sure. There's actually the QR code here, and that'll take you to our GitHub repo that has the initial instructions for how to get started. And what to give an idea of our timeline, the interns last week is next week, and we're going to spend next week going through documentation and making sure that all the repositories are in tip-top shape. And at that point, pretty much anybody who wants to download this and give it a shot is more than welcome to. We're going to be doing an alpha deployment here on the University of Michigan's campus. And obviously, with all things new and especially open source, we expect that there to be some changes, hopefully minor. I think we've got the solution 85, 90% done now, and now we just need to sort of refine it. I
Okay.
I could scare up that URL. Could one of you throw the documentation URL into chat, please?
Okay. And while you're doing that, I guess sort of a question on sort of your field deployment strategy and what you've learned so far. Has this found anything interesting? And by interesting, I mean maybe it was unexpected, it wasn't a use case that you were looking to sort of capture, or has it been useful in fixing any particularly persistent problems that would have gone unnoticed?
We have not had an opportunity to do a field deployment with this version of the software to kind of diagnose any sort of problem, persistent or otherwise. That's going to be the next couple of months' work. We actually own a dozen or so of these probes. We bought them pre-pandemic, which was very fortuitous because during the pandemic you couldn't buy these for love or money. And we're going to be doing that over the next couple of months, trying to work out any sort of bugs in the system.
Okay. And it looks like you've standardized on the Raspberry Pi 4 hardware. Is that sort of what you're going to be using going forward, or is there any indication of going to the next generation or whenever that happens to come out?
Well, there's a reason that all of this stuff was specifically chosen, and it's sort of the center of a Venn diagram between operating systems the hardware will run, operating systems that perfSONAR will run on, and the availability of the hardware. So the Raspberry Pi 4 is able to run Ubuntu 22. It's also something perfSONAR can run on, and it had good support for aftermarket hardware like cases and whatnot. I suppose it's conceivable that we could move to a Raspberry Pi 5, but currently, from what Lou tells me, it's not supported by Ubuntu yet. So, what 22, excuse me, 22. I think it might be supported by 24, Lou, but it doesn't support 22. So perfSONAR right now runs on Ubuntu 22. So that's kind of where we're at. That's kind of like the sweet spot. Also, I'm not sure what running on a Raspberry Pi 5 would buy you more than a Raspberry Pi 4. They both have the same Wi-Fi radios. Uh, you don't really need increased performance to monitor Wi-Fi. There's not really an advantage for a higher CPU clock because everything is obviously running slower than your Wi-Fi radio, period. Um, and they probably are a little less efficient for energy consumption. But I suppose as time goes on and the 4 is phased out and the 5 becomes the flagship, hopefully we're able to, run perfSONAR on it, run perfSONAR is going to go Ubuntu 24 eventually. And at that point, it'd probably be more feasible for us to use a Raspberry Pi 5. I see
Okay.
Abigail. Abigail has a question.
Yes. Well, I also have a comment. I was just gonna say, I remember building some of these Raspberry Pis in my bedroom in the summer of 2020. So I'm really glad to see that the project continues and giving them to you in a University of Michigan parking lot. So I'm glad to see that it continues to pay off. I'm really excited to see this get deployed as well at the University of Michigan. Um, my only comment is I think after the alpha deployment, if it proves to be viable and things are looking good, I think it would be a good idea to publicize this to students and allow them a way to submit feedback on where Wi-Fi is bad. Because there is nothing students love more than complaining about M wireless. And so I think even just the perception that we're like doing something about it and working on it is a very positive win for everybody.
Well, that's a great suggestion, Abigail. And I do remember during the pandemic, a quick handoff in a parking lot. So, we weren't vectors for the plague in order to get some Raspberry Pis into the lab. And we still are using Abigail Fox built Raspberry Pis. So thank you very
Oh,
much.
wonderful. Because some
Yes.
of those were a real pain.
Yes, those armored pies with all them tiny screws. So
Yes, they are built to withstand students poking them to see what they are,
that
which
is
was
correct.
actually one of the considerations when we were first picking out cases and configurations and stuff is if a student sees this and wants to poke it, is it sufficiently durable that it won't get damaged just by someone being like, huh, what's this? I'm gonna touch it. Um, yeah. Anyways, I'm very excited for you guys. I hope you really enjoyed working on it this summer. I really enjoyed getting to be a part of kickstarting it, and I am so excited to see that it's at the point for an alpha deployment because I know that required a lot of hard work. So congrats, guys.
Yeah, very good work.
Thank you. Thank you.
We don't have any other questions right now, so I'll put out another pitch. If anybody has a question, raise your hand or unmute or put it into the chat room. I already have the slides. Thanks, Ed. I'll make sure that those get posted along with the video. Looks like we may be out of questions. So thank you all for going through this. And since you're about to not be interns anymore, good luck with the rest of your studies. And maybe we'll see you next year when Ed comes back and has another talk about the status of pSSID.
Yes, this seems to become an annual tradition.
All right. Well, thanks everybody. Next week will be perfSONAR open office hours for those that want to join and ask questions about perfSONAR 5. So we will talk to everybody next week. Thanks, everybody.
Thank you for
Jason.
hiring us.